Our today's speaker is Professor Jaesun Lee, the head of non-destructive evaluation and structural health monitoring laboratory in Changwon National University. Today, he will tell us about phononic crystals for elastic waves manipulation. So, Professor, the stage is yours, up to 1 hour with all questions. So, please share your screen.
Okay, thank you. Yeah, today I'm going to talk about the phononic crystals. So yeah, I'm gonna share my slide first. So everybody can see the slide, right?
Yes, we can.
Yeah, thank you. Yeah, so as I am introduced, so my name is Jaesun Lee. I'm working at School of Mechanical Engineering, Changwon National University in South Korea. So I'm running the NDE and SHM lab in the university. So today I'm going to talk about phononic crystals for elastic waves. So yeah, before I start my presentation, I just want to briefly introduce about my Changwon National University in South Korea. So this is South Korean, the peninsula, Korean peninsula, and the city Changwon is located at the southern part. It's near the Busan area, so it's about 30-40 minutes by car from the Busan. So as you can see here in the downtown of the Changwon city, so half of the city is about for the industrial complex, and another half is for living and university and all other the administration office out there. So this is really the national industrial complex. So we have a lot of the large companies located in Changwon together. So this is the picture of Changwon National University. So the university begins at College of Education in 1969 and become Changwon National University in 1991. So we have a bunch of the different department and colleges in our university. So also, as I mentioned, this is a really good location for the engineering department. So because we are in the center of machinery industry, including heavy industries, for example, Doosan now is a Doosan Ability and LG Electronics, Samsung, Hyundai, and all those big companies are located in Changwon. Yeah, this is beautiful pictures that our university. So the every different seasons we have whole different scenery of the landmark in Changwon, especially in our university. Yeah, and this is our lab. So I'm running ND and SHN lab. So we are basically do a lot of research for ultrasonic ND and SHM, and also we do some theoretical the the approaches. For example, metasurface or for phononic crystals. We also do a lot of signal processing for ultrasonic signals and images. So these are the project and organizations and companies we are working together. So we run several research projects funded from the government and also funded from the companies. Okay, now I'm going to start about the main topic of today's the talk. So we do the research of phononic crystals. So as you can see here, phonon is the mechanical analog of the photon. So those the importance of phonon in fundamental and applied research goes far beyond the common understanding of sound. So full phononic spectrum span a broad, mostly large range of frequencies from the few millihertz up to the dozens of terahertz. The acoustic wave phonons are informations and energy carrier that plays an inherent role in consider matter physics. So we use this phonons for to the some sort of research. So so two generally built blocks that are used for achieve the goal of the manipulating wave propagation in solid. So first, the Bragg scattering and local resonance. So first of all, so imagine that the wave that indicate incident of on the scatter, which is excited after interaction with the wave and starts to radiate the wave. So so those waves will be propagate along the these phenomena. So these are really well known uh, the interactions. So we can see we have seen that periodic structures can have an influence on the propagation of the waves. So these are the equations. So we consider there's a two coupled oscillators. So it move up and down. So it will make a waves to propagate from the one to the other. And beside the Burke wave, so the guided wave exists. So depending on the shape of the waveguide, the guided wave are divided into plate wave and cylindrical wave. So plate wave are SH and LAM waves for the cylindrical object, torsion wave, fractal wave, and longitudinal waves. The key difference between Burke and guided wave is multimode behavior of the guided waves. So one thing I want to mention here is SH0 mode is non-dispersive. As you can see here, this is dispersion curve. So you can see here the SH0 mode is non-disturb, non. So so constant phase velocity and group velocity are for the SH0 mode. This is key feature of the SH0 mode. So the first torsion mode have the same behavior in cylindrical structures. So these are the simple movement of SH mode, SH waves, and antisymmetric mode and symmetric mode in the plate. So these are the torsion mode and the flexion mode in the cylindrical structures.
Jason, I'm sorry. Can I ask a question? Mikhail Petrov.
Yeah.
From the previous slide. So the right figure is just for a plate or for the cylinder. That's what I didn't get. The dispersion curve.
This dispersion curve. This is for the plate. So in the plate, we can have a LAM wave, which is a symmetric and anti-symmetric mode, and also there is a SH mode will be the added will be exist. So in this dispersion curve, we can see symmetric mode, anti-symmetric mode, and also SH mode. So for the cylindrical structure, the shape of dispersion curve will be a little bit different.
Okay, I got it.
Okay, yeah. So yeah, so LAM wave has a S and A mode, symmetric and anti-symmetric. So phononic crystal allows to switch between the mode. So numerous studies in ultrasonic testing field shows that different modes has a different defect sensitivity, and phononic crystal simplify the analyze between the because of the one mode. So as you can see here, so in the LAM wave there is a whole different wave modes will be appear in the dispersion curves. So but from the some of the periodic structures can phononic crystals can generate the band gap here, so we can neglect some part of the wave propagation phenomena in the in certain range of the frequency. So also we can if we can well tune the shape of the structures, then we can select certain wave mode that we want to neglect. So because we can tune the band gap frequency ranges. So these are the earlier the researches. So another application of phononic crystal is we can make it as a mechanical lens. So as you can see here, if we make some sort of the phononic crystals, so we can arrange on the surface of cylindrical structure. So once we generate a wave, so the wave will be go through these structures, and then those structures will be act like a mechanical lens. So the wave will be focused on the certain area. So after these filters, so it goes to the certain it act like a focusing theories. So we generate the torsion mode, and then it will propagate that will be focused on the top surface. So this is more like a phase array techniques, but based on the phononic crystals, it can act like a mechanical lens as well. And another application is energy harvesting. So increase the output can also be achieved by the defective phononic crystals. So under defective phononic crystals, assume that break in the periodicity. Here you can see the increase of the outputs. So we generate the wave. So after the wave go through here, so as you can see here, the energy will be increased at a certain frequency. So we can have more energy in that because of these special structures. And another examples are about the it will act like a waveguide. So based on the certain excitation frequency range and also the shape of phononic crystals, so we can make the special direction of waveguide. So if we generate a certain wave, so the wave will go through here, or it turn to the other side, or we can control the wave propagation directions. So these research are already have done by other the early researchers. So also this is really good applications. And another application of the phononic crystal is mechanical filter. The band gap is a fascinating characteristic that finds application in the various fields. One of which is its role as a mechanical filter. So you can see here that early researcher have do the research of the it generates certain frequency range, and then once we analyze the waveform and then to the frequency range, so we can see here the excitation frequency and with the higher harmonic components, so which is we call the nonlinear terms. But if we have certain shape of periodic structures or phononic crystals, so after it go through, the waveform will be distorted, and then once we check the frequency spectrum, so you can see here the fundamental wave, the excitation frequencies contains here, but you can see here, interestingly, second harmonic the frequency range is filtered away. So that is, as you can see here in the graph, because of here that range 95.53 and to the 109.6 kilohertz will be filtered. So you can see here the second harmonic frequency range will be it will disappear. So we can use this kind of the the characteristics of, and then we can use it as a mechanical filters by these structures. And this is another application of a mechanical diode. So another example is a mechanical diode. So here, the presented phononic crystal with a varying depth of the A0 mode to prevent propagate in backward direction. So it will control the wave propagation directions. So only A0 mode will not go through. But we can see here in this figure, the wave will go through to the end. But if we generate the other side, the wave will not go through the after this structure shapes. So we can control the wave propagation direction only to the one side. So this is also can be the one of the examples. Yeah, and the other example is a wave transformation. So, so we think of we want to generate a certain wave mode.
Can I stop you here? Can I ask a question from the
Yeah,
previous slide?
sure. This one?
Right. But this is not the but this is the reciprocal system, right? Yeah. So it's not like so it's not nonlinear, neither time nor varying. Yes. So what you're showing here, just reflection coefficient is different, right?
Yes, that's right. So one side is it propagate through that, but the other side is not.
Yeah, but the transmission should be the same, right? Because you have a reciprocity principle.
Yes, but because of see here, because of this structure shape is varying from the one side to the other. So that's why that it will filter by this structure.
Okay. And also, since I already asking a question, sorry, we usually try to ask questions while during the seminar. I hope you don't mind.
Yeah, it's okay.
Yeah, from the previous slide when you were showing filtering, yeah. So I clearly understood the idea of this filtering because there is a band gap, but why the other harmonics are not distorted? There is a huge dispersion in the system. So the modes, the frequency which are passing, they should be somehow distorted, or how? Why doesn't it happen?
You mean why the frequency contents is not shifting to the other frequency range, right?
Yeah, so for example, something can happen with the other modes, with the other frequencies, because you see on the left there is a very complicated band structure, and some modes are slow and some modes are faster. It's also will lead to your package somehow disturbance. Maybe that's because the filter was very short, or how?
Yeah, so that's why you can see here that time harmonic signal is quite different, right? Because there's a huge distortions. But once we see the frequency spectrum, so you can see here the amplitude, the magnitude of the frequencies contents are different. But as we designed here, as this researcher designed here, the band gap is properly works. Yeah.
Okay. All right. Thank you. Oh, sorry for the interrupt.
Oh, it's okay. Yeah. Yeah. So yeah, I'm coming back to wave transformation. So if we want to generate certain wave mode, so we need to tune the wave mode, or we have to find the proper way to generate a certain wave mode. But if we use this wave transformation method, then we generate a certain wave mode, and then it will transform to the other mode. So okay, so in this case, so SH mode and torsion wave. So in the there's a three way to generate the last wave: the PGT plate with a specific, the uh, the PGT plate of the certain the movement of directions, and the EMAT and and the other method. So so if we generate a certain wave mode with this special shape of uh, the phononic crystals, after it go through, so the wave will be distorted to the other the wave mode. So this is also one of the good application of the the phononic crystals. So here, as you can see here, there's so the so the structure of uh uh structure of the arrangement of atoms in the nature crystals and the result in phononic features typically typical of typical for the these kind of structures. So we can see here this is a we simplify so one's unit cell of the structures. So these are the appearance of the second order of Brilliant and modification of the phonon dispersions. So as you can see here, so if we use the wave of the guided waves, the lemon wave and SH wave mode, so you can see here red line and then blue lines here, and then each the wave mode have a different the frequency range of the band gap. So you can see here the below the 50, so there is a one SH wave band gap here, and the one really small range of between 50K to 50 hertz to the 100 hertz, and so another SH mode and Lem wave dispersion and Lem wave of the band gap here. So we can calculate all those those method. So we see that how we do the this kind of research. So in the beginning, so we made the framework of considering the pure torsion wave propagated in the infinite array of phononic crystals. The main question in this study is to understand how phononic crystal affect torsional wave propagation. The dispersion curves can be calculated by applying the flux boundary conditions, as you can see here. So we assume that there is a the whole many of the infinite number of the phononic crystals. So we use simple of the unit cell here. So you apply the flux boundary conditions, and we can calculate. So we can calculate the dispersion curves. So we do this research by the commercial package of the COMSOL. So these are the the parameters we when we calculate this dispersion curves. So as you can see here, the change of torsional wave behavior behavior is significant. The first mode become dispersive because of, as I mentioned, for the cylindrical structure, the first torsion mode is non-dispersive, but because of these structures added on the surface, so the first torsion mode is dispersive. Apart from band gap, the negative group velocity negative group velocity can be observed. So you can see here, the slope of at this range is a negative direction. So each frequency range, the disbursement, the distribution of the structures can be seen here. Okay, so this is the once we calculate this problem, so this is time domain simulations. So you can see here the 80 kilohertz case related to the band gap. So you can see here we calculate this band gap spectrum. So you can see here if we generate 80 kilohertz, so there is a band gap range. So the wave will generate here, but it cannot go through the this the phononic crystal the structures. So you can see here the wave come here, but all the wave will not go through the these structures. On the other hand, if you generate in different the frequency range, which have the wave propagate, and we can see here group velocity here. So the wave generate here, and then it go through the phononic crystals, and then it go to the end, and see here this is an instant wave in red color, and the blue color is the wave pass through the periodic structures, phononic crystals, and this is small reflections from the periodic structures. So it goes through some parts still have some reflections. And interestingly, so we have a positive and negative group velocity at the same frequency range. So you can see here, the wave will come into this direction. So some part of the wave will go through, and some part of the wave will be can see here, and it will go back to the negative directions. So this is the about 340 kilohertz of the excitation frequency range. So to confirm it, the two-dimensional Fourier transform was performed, which is matched with the calculate dispersion curves, and negative slope can be identified here. So you can see here, this is a negative slope. So this is really exists. And the other case is a phononic crystal for the SH wave. For the given geometry, as you can see here, the dispersion curve was calculated, and several band gaps for SH wave is highlighted here. So as you can see here, the gray area is SH wave band gap. So as you can see here, but it's kind of interesting that because we have a lambda wave and then SH wave, but we still can see here some range of SH wave band gaps. So we confirm this. We try to confirm this theories and the simulations. So we do the experiment for these structures. So you can see here, this is a phononic crystal array of phononic crystals, and we attach on the the aluminum plate, and avoid some deflections from the reflection from the others directions. So we use try to make absorbing boundary. So we attached clays, so it will absorb a lot of the reflections. So there's a the emitter, and this is a receiver. So we generate the wave, and we receive the wave after it goes through the phononic crystals. So this is the experimental data. So you can see here the prediction predicted band gap slightly shift. So because of in the simulation, we have the aluminum plate, and there is a phononic crystal the plate on above to that main plate. But actually, to attach that, so we use epoxy to attach the main plate and the phononic crystals. But in the simulation, so we that the epoxy layer is not included in the simulation. So that's why we have a slightly the shift to the some in the frequency range. But except that actually it's a pretty well matched. And the other case is the temperature sensors. So everybody can see here the material parameter depends on the temperature. So the band gap, but the band gap configuration should also rely on the temperature. So from one point of view, so the temperature variation can be undesirable because most of the studies are made at room temperature, and the drift of the material property is unwanted, because that's, we already, everybody just, assume that the material properties at the room temperature. But in the real field, actually, we have to consider about, temperature ranges. So this is one research for the, how we can act, like how we can measure the temperature variations with these phononic crystals. So you can see here, from another point of view, so it can be used to match the band gap configuration with the exact temperature. With the increased temperature, all modes trend to the lower frequencies. The exceptions that describe a decreased density and Young's modulus. So that is decreased sleepiness and math. So you can see here. So once we change the temperature, and it will affect to the material properties, because it was slightly changed. So you can see here the wave, the disperse curves will be slightly changed because of temperature changes. So if we use this phenomena, then we can use this one as a temperature sensors. So to establish the sensitivity of the wave, so you can see here the detail of the F. So that is, we compute, we calculate all those different material and at the different temperatures. So you can see here that it's at the room, from the room temperature to the high temperature. So the temperature increases, so the gap between the band gap size will be will be changed. So we can use this this characteristic as a and then we can use these informations use as a temperature sensors, because it will have a different range of the frequency gaps. And another application can be the meta filters. So conventional ultrasonic testing based on the linear assumption and the spectrum have only fundamental frequencies. But most of if we look into the frequency range, so all the material and all the equipment and the transducers, they all have nonlinear behaviors. So the so the entity and NDE. So we have we do the the research for the nonlinear ultrasonics, and we look into the the nonlinear terms, the higher harmonics. So the here all the experiment shows the sensitivity of the higher harmonic on the micro inhomogeneity and inclusions. So as you can see here, so if we think about the lifetime of the material, these are the once the material is damaged and it start have cracks, and we will go very fast to the cracks failures. But in the nonlinear ultrasonics, even there's no defect, but we still can measure the change of the microstructures or the material behaviors. So the source of nonlinearity can also be from the electronic devices, electronic equipment, or contact adhesive conditions, because of the transducers and specimens are not perfectly attached well, and because of the micro structures of the materials. So all those sources affect to the nonlinearity in the structures. So we suggest metafilter for for this research. The key feature is higher frequencies. But in the most of previous the researchers, they do a lot of similar research, but it's really low frequency. But for the NDE, or if we want to use in the real field, we need to increase the frequency range. So in this the setups, so we focus on the higher frequencies. So after so we set all the parameters, and we calculate this model. So you can see here dispersion curves are different material for the different materials: aluminum, steel, and copper. So in these three cases, the band gap at the frequency are mostly the higher than 300 to the 500. It's above to the 500 kilohertz. So that means we can filter some higher frequency range. So that is actually we can bring it to the real field. So you can see here the frequency with respect to the height of the structure. So we can see here the frequency range of the band gap. So lower frequency and upper frequency. So you can see the gap between these two frequencies range. So the size of band gap we can see in this graph. And this is another application. So the membrane resonator shows a promising result in noise cancellations. So we use the special shape of.
Yeah, I'm sorry for the previous slide. Yeah, so maybe I'm missing something, but when you mean this nonlinear filtering, so where is the nonlinearity here? And maybe I'm missing some point.
Nonlinearity is always exists from the here, as I mentioned, from the electronic equipment.
What are you trying to filter? So I understand the nonlinearity occurs at the high intensities. Now you are showing the meta structure, which has some filtering options. But so how it's connected, how is this filter is connected to nonlinear effects?
Because of the higher harmonics, say they have like a double and triple. So if we generate like a certain frequency range, for the low frequencies, it's okay. But if we generate like a few hundred kilohertz, and then second and third harmonic will be like a few hundred or thousand. So that's why we need to have a higher frequency the band gap. We need to achieve this. This is our goal. So that's why we use certain the shape of the structure. So we use this the structure as a meta filter, because we make a certain some sort of those structures with the special shapes.
So you want to filter out the higher harmonics? Is that it?
Yeah.
So you want, so because it's high intensities, your higher harmonic are generated and you want to get rid of them, right?
But actually that is it's a bit different way. So always the nonlinearities exist from the equipment, and then the transducers and also material itself. But if we want to focus on the just the primary wave, primary frequencies, then from the generation, so the way we propagate to the directions. So we need to filter all the higher harmonics, and then only the primary frequency will be just propagate.
I see. It's more just for your testing system being more accurate. You want to work only with one frequency range.
That's right. Yes.
I see. Okay. Thank you. Yeah. And what is the amplitude? So as I understand, the nonlinearity by itself appears because of unharmonicity of atomic oscillations, right?
Yes.
So at some amplitude, when your amplitude is large enough, you cannot consider your system as harmonic anymore.
You still need to consider the higher harmonics because it will generate some because of that the system problems. Yeah.
And what is the amplitude of the field, like in any units which are required to observe nonlinear effects? Is there any
for the the frequency range, actually that is really small magnitude. Yeah. But actually it still affect to the the wave signals.
Okay, so it's something like what's the I don't know the power of the meter, watts or units of watts or how?
You mean generation?
Yeah. So
Yeah. So for our experiment, we use like I think it was like a 400 voltage generation. Yeah.
Okay. All right. Okay. That at least gives me some understanding of the of the numbers. All right. Thank you.
Yeah. So these are the noise cancellations. So it also it can also be used in vibration suppression. So here is a design of our resonator here. So firstly, the dispersion curve was calculated. You can see here the dispersion curves, and so we treat the resonator as a phononic crystal in the simulation. So we can see the band gap from 100 to the 150 kilohertz. Also, the curves transform to a straight line. So indicating the resonance of the response of the resonators. Here you can see that the dispersion curve of the tube is 0. So you can see it will change. So you can see here that we designed the special shape of the resonator here. So based on the the modes, so you can see here the different the movement. So we print out because the shape is complicated. So we use silicon the 3D printer. So we print out this the structures and we attach on the small tube and we generate wave. And then you can see here the so here the black line is bare pipe tube and the red line is with the resonators. So you can see here the peak frequency of the bare tube and with resonator tube. So it will shift and it will decrease. So the second flasher mode here, and we can see here the band gap between 100 to the 150 kilohertz. So actually, the single resonate give the amplitude drop like 22 to the 24 dB. So actually, it also it works pretty well. So potential to achieve the band gap lower than 50 hertz. So we can design we can change the design or we add more resonators so we can increase the performance of these special structures. Yeah, so today I introduced so many cases, examples of the phononic crystals and its applications, and also I just introduced some the research result of our research on the phononic crystals and its applications. So ultrasonic testing can be enhanced by applying the phononic crystal to suppress higher harmonics or focusing or uh, the vibrations. So and drift of the band gap configuration can be used as an indicator of temperature changes. So, you know, even we have the same structure and same shape of phononic crystals, and we can change the viewpoint. So we can apply as a, you know, the suppression, or, you know, monitoring of the temperature changes. So these are the, you know, our way, our you know, think of the, you know, how we can expand this research, and how we do the, you know, find more applications. Yeah. So yeah, thank you for today's talk. So is there any question? Please. Yeah.
Thank you, Professor. Dear colleagues, do you have any questions? Please ask. I've got one. Could you turn on slide 25?
Okay. Yeah.
No, maybe previous with experiment.
Okay.
With experimental results. Yeah, here.
Yeah.
And maybe one slide before, where you talked about layer, am I right? You talked about the epoxy layer between transducer and the plate. Maybe it was slide 26.
You mean
Yeah,
the result?
yeah. But
Yeah.
you talk about possible explanation of differences between experiment and numerical simulation. Yeah, am I right that you mean epoxy layer between transducer and the plate?
Oh, no, I will explain. So as you can see here in this model, there is a, you know, the main plate, and here this is the phononic crystals. So we you know, manufacture the, you know, the phononic crystal structures, and then we attach that structure on the plate. So those, you know, phononic crystals and plate will be, you know, use the epoxy to attach this structure, the two plates together. So you can see here, this is the aluminum plate, and this is the phononic crystal plate. So we use epoxy to, you know, bond these two plate together. But in the simulation, there's a, you know, that the epoxy layer is not considered. So that's why the result is slightly, you know, different, but still it's a really, you know, well matched.
Yeah, thanks, understanding. Anybody else? Questions?
Maybe I still have one, though I already almost occupy the scene today. But yeah, thank you, Jason. Very interesting talk. It's really very educative for me as well. But I have a general question. So you said you work on industrial projects as well, right? So what is so how big is your team, and what is the division, like, let's say, I don't know, in funding or in resources coming from industry and from research, from pure, let's fundamental research?
So our team is you know, it's about 10 people in, you know, in my team. So there's a postdoc researchers and PhD students and master students. So as you can see here, I got, you know, several, you know, research project from the government, and one is a really, you know, pure scientific research of, you know, one is a make some simulation model for the, you know, the multi-scale the wave propagation problems. So we try to, you know, make some model for the, you know, if there's a, you know, nonlinearity in the structures, how we can, you know, apply this one into the, you know, simulations. Yeah. So that is the one project. The other one, and mostly the government project is, you know, pure scientific engineering problems. But those, you know, the fund from the companies is so more like, you know, data analysis, and while they are developing their the new product, they found some problems, or, you know, some interesting things. You know, they have some the maintenance problems. They already have a lot of, you know, their products, and they have some the maintenance problems. So they try to find how we can find the problem in the you know in their product and in the field. Yeah. So we try to find how to measure you know that problems in the so one is like a yeah air conditioning, yeah, energy electronics, and also you know like a yeah yeah so yeah so various of the research, and also I'm still thinking about today's talk, and also these some of the our research outcomes can be you know applied to the you know those industrial field. So especially for the you know those companies, they are you know they always consider about you know the problems of vibrations, you know, because of their all the you know the complicated components. They have you know the vibration problems, but they have a you know limited uh, the room for the you know the changing the designs. So
Okay.
those research can be applied for the those applications as well. Yeah.
Okay, thank you.
Sergey, you're welcome.
Yeah, hello. Thank you for the talk. Regarding this, like industrial and other applications, so maybe I missed that, but how fragile are these structures? So I mean, they're made of this small cylinders, for instance, and well, if you apply some mechanical pressure, yeah, so from some outside, yeah, so will they deform somehow, so or not? I mean, how the structure will behave if you apply some external mechanical force?
You mean those industrial applications, their products?
Yeah, I mean, so if you have some of the structures and, well, in kind of real life applications, it's possible that they can be damaged by some, I don't know, by something, yeah. So especially if we talk about, I don't know, some big scale things when they're not isolated.
Yes, actually, yeah. Some research group, they try to you know apply this kind of method to the you know actually in the real field, but still there is a you know some gap between the lab research and the real field applications. But you know because of we try to correlate between those you know those conditions about the you know the working environment, and also you know try to you know connect the our research result, especially for the you know wave propagation amplitude or you know or other things, and then so that is still you know ongoing project. So so one so yeah it will be possible actually, but still you know there is a gap between you know real industrial applications and the researches.
All right, so maybe a bit related question. So how hard is it to reproduce the structures? I mean, so when you manufacture them, so what is the typical size of defects? Yes, so because obviously there should be some displacements, or the cylinders will be not of the same size. So what is kind of this size difference between the model and the manufactured thing?
I mean for the defect for the experimental
Yeah.
defect.
So, for instance, in the model, you have a period of I don't know some millimeters or something. Yes, and when you produce the structures, obviously there will be some error in manufacturing. Yeah, so the period will not be constant, for instance, and there will be shift of the cylinders by some fraction of millimeter or something. So how large is this error, manufacturing error?
Yes, actually. So as you can see here, for example, so this is the thing we manufactured. So there is a like these structures are like a few millimeters. So the errors is it's a pretty small, and it depends on if we have to consider really precise manufacturing, and we have to consider really small errors for the structures, then we can manufacture it, but it takes time, and we need to have a better the equipment. So that at this moment, actually, the errors of the manufacturing is not a big issues for this research at this moment.
Yeah, all right. Thank you.
Any more questions? Anybody? If not, I would like to thank Professor Lee. Thank you very much. It was my pleasure to hear your talk.